In this video, we present a fully automated deep learning-based segmentation of normal, infarcted, and edema regions for multiple cardiac MRI sequences. Late gadolinium-enhanced imaging is one of the commonly used cardiac magnetic resonance sequences to diagnose myocardial infarction, a common cardiac disease that may lead to heart failure. Acute injury or inflammation related to other conditions can be detected using T2-weighted CMR. However, detecting ventricular boundaries using LGE or T2-weighted images is challenging. While this function can more easily be performed using a balanced steady-state pre-position sequences. Often, many cardiac patients are scanned using multiple CMR sequences, and utilizing the combination of these sequences will allow for obtaining robust and accurate diagnostic information. In this study, we utilized deep convolutional neural networks to delineate left ventricular blood pool, right ventricle blood pool, left ventricle normal myocardium, left ventricle myocardial edema, and left ventricle myocardial scars. As shown in the figure, our proposed method is fully automatic and utilizes no additional data other than the training set provided by the challenge organizers. The details of each module are introduced in the following sections. We first extract the input data in a slice-by-slice manner and perform center cropping to obtain images of size 256 by 256. To improve the number of samples, we perform two data augmentation schemes including random warping and random rotation. The random warping is performed by first generating a 8x8x2 uniformly distributed random matrix, where the last dimension indicates 2D space, with each entry in range -5 to 5. We then resize the non-rigid warping matrix to the image size with dimension 256 by 256 by 2 and apply the warping map using bilinear interpolation. The extracted input CMR slices and the labels are warped 20 times. After augmenting the data using random warping, we then utilize random rotation in 90 degree, 180 degree, and 270 degree with equal probability. The training set is then augmented with 1 time more data with random choice among the 3 options. All training and validation images are normalized using 5th and 95th percentile values of the intensity distribution of the 2D data to obtain relatively uniform training sets. We encode the augmented input and label stacks and produce 5 input blocks as shown in the right figure instead of blindly concatenating the CMR sequences, where each block represents the data used to train the target class. The 5 input blocks are LVBP block, which uses BSSP as the input, and LVBP as the target. RVBP block, which uses BSSP as the input, and RVBP as the target. LVMP cardium block, which uses BSSP as the input, and the linear combination of LVBP, LVNM, LVME, and LVMS as the target. LVME-MS block, which uses LGE as the input, and the combination of LVME and LVMS as the target. And the LVMS block, which uses the T2 as the input and LVMS as the target. In the testing mode, the linear encoder will perform on the input stack. The network module will infer on the encoded input, and the decoder will extract the predictions after the post-processing. The unit module utilizes a shallow version of the standard unit to prevent overfitting. The unit is trained on all the 5 input blocks produced by the linear encoder. The loss function of the unit is selected as the negative dice coefficient with atom optimizer. The Mascar-CNN module utilizes ResS50 as the backbone for the segmentation task and is implemented using the Matplotlib library. The Mascar-CNN is trained on the LVME-MS and LVMS using atom optimizer. The Unit++ module utilizes VGG16 as the backbone. The model is trained on the LVME-MS and LVMS using the negative of dice coefficient as the loss function with add optimizer. The row predictions from the treat networks are averaged for LVME plus MS and LVMS and followed by binary activation with threshold 0.5. We applied post-processing to retain only the largest connected component for the predictions of LVBP and LV epicardium by unit. The operation is performed in 2D space with a slice-by-slice manner. In addition, we applied an operation to remove holes that appear inside the foreground masks. The post-processing is performed on the encoded predictions before the linear decoder. The corresponding decoder performs the linear subtraction on the predicted masks of LV epicardium and LVME MS and is followed by binary activation for all predicted masks in 5 target classes with threshold 0.5. The decoder also includes a binary constraint for the LVME and MS predictions by calculating the myocardium mask using the predicted LV epicardium and LVBP and performing a pixel-wise multiplication. In the equation above, sigma denotes the binary activation with threshold 0.5 and the center dot denotes the element-wise multiplication. Pi tilde denotes the predictions after post-processing, and Pi denotes the final prediction masks. The training set consists of 25 cases of multi-sequence CMR, and each refers to a patient with 3 sequence CMR, including BSSP, LGE, and T2. The training data is processed using the MVMM method. The proposed method is evaluated over images acquired from a total of 20 cases and is performed by the challenge organizers with dice score on LVME plus MS and LVMS. The ground truth of the test sets are not shared with the participants. The best result of our proposed method achieves a mean dice score of 46.8% for LVMS and 55.7% for LVME plus MS. Our proposed method, network module, improves the overall performance of MS and ME plus MS by comparing our proposed method without the linear encoder and decoder with the unit. Our proposed linear encoder and decoder module further improves the performance, especially in the MS segmentation. The improvement is also reflected in box plots. In conclusion, we propose a fully automated approach to segment the LVME and LVMS from multi-sequence CMR data. We introduced an augmentation module to enhance the training set and linear encoder and decoder along with the network module to improve the segmentation performance. The algorithm is trained using the 25 cases provided by the challenge organizer and evaluations performed by the challenge organizer on another 20 cases which are not included in the training set. The proposed method yielded an overall mean dice metric of 46.8%, 55.7% for LVME and LVME plus MS delineations. These are some of the references. Thank you for listening.